Welcome to today's lesson and our new unit, Unit 4, Derivatives of Exponential and Sinusoidal Functions. Lesson 1, we are going to learn about rates of change of sinusoidal or trigonometric functions. Just as a reminder, a periodic function is when the y values in the function repeats at regular intervals. So we can predict the y values and when it will occur because it will repeat itself. A sinusoidal function are functions whose graphs have the same shape as a sine wave. So here we have a sketch of a sine curve. So this is sine of x, and P and Q are 2 points along the curve that are really close together. So we have a line that goes through it that is representative of the tangent along the curve. So let's move this tangent along the curve and see what happens to the slope of the tangent. As we can see, right here we have a positive slope, and as we move along the curve, it is still positive. However, it starts to decrease in steepness. Okay, so right there, okay, so at the top here we have a slope of 0, and as we go further and further down, we're starting to now become a negative slope. Okay, so it's a negative slope, but still pretty steep. It's getting steeper, steep, and it's the steepest right there. Okay, so it's the steepest right there, but a negative slope. So let's keep moving. Okay, so it's going to now reach 0 again. Okay, and then we're going to start to increase, and now I've lost my curve. Okay, so it seems like I've gained my curve back. So, if we keep moving, okay, so it's now back to a positive slope. Okay, and it is probably the steepest right there. Okay, and the process will repeat itself again. Observe this dot that I've placed on the curve. This dot is a representation of the slope, of the value of the slope of this tangent. Now we know that the slope of the tangent is going to change as we move along this curve. Okay, see what happens. Okay, so here I am moving along the curve. Okay, let's just do this a little bit better. Here we go, and I'm going to keep going. Right here, I'm going to reach a 0 point. Okay, so remember, this is the slope, and what it's actually doing is scribing out the shape of the function of the slope of the tangent, so our derivative, essentially. So right there, we have a 0, which is a maximum point on the curve, which is the flat line. Our tangent is a flat line. So we keep moving along, okay, what we'll notice here is we're at a negative slope, and it's going to be the most negative. The derivative is going to be the most negative. So that's going to be a minimum rate of change. Here we're going to head back up to 0, okay, because our tangent is flattening out, and then at a maximum point, at a maximum point right there. The curve outlined in pink is our original function, f at x is equal to sine of x. In red is our derivative. So it is the function that describes the slope of the tangent of this curve. Do we recognize this curve, what it looks like? Well, to me, number one, it's sinusoidal, okay, and periodic. Number two, to me that looks a lot like the cosine curve. So we can conclude that the derivative of a sine function is then a cosine function. So just to summarize, the derivative of sine and cosine functions. The derivative of y is equal to sine x is then just cosine of x. If we were to have plotted cosine of x and performed the same investigation, we would have found that the derivative of cosine of x would have scribed out the curve of negative sine of x. Let's take a look at some of the simple rules involved in differentiating sine and cosine functions. Okay, so the first rule we're going to look at is the constant multiple rule. So if there's a constant out front, we would simply pull out the constant out front and just derive the function behind the constant. So in this case, this example here, 3x sine x, or 3 sine x, is equal to dy by dx is then just 3 cosine of x, okay? The sum and difference rule, remember that if you have two functions that are either added or subtracted, then we can simply just look at each of those functions separately, derive them, and then just find their sum or their difference. Okay, in this case, I'm going to go y primed, okay, is cosine of x, it's the derivative of sine of x, and minus sine of x. Okay, and that would be our derivative. So here we can apply both of the rules, okay, dy by dx is equal to negative 2 sine of x, okay, minus 4 cosine of x. And the only thing that we could do here, I always look to see if there's anything that I can do to simplify. In this case, I could, if I really wanted to, factor out maybe a 2, okay, and that would leave me with sine okay, and a 2 cos of x. Okay, and that would be our final answer. Let's look at our first example, example number 1. We want to find the slope of the tangent to the graph of f at x is equal to 3 sine x at the point where x is equal to pi over 4. Okay, so the first thing we want to do is we want to find the slope of the tangent of the graph. Okay, so when we hear tangent, slope, we want to take the derivative. So first we want to take the derivative of our function. Okay, so f primed at x is then equal to 3 cosine of x. Okay, so that's our derivative, but we want to find the slope when x is equal to pi over 4. Okay, so pi over 4, what we're going to do now is 3 cosine of pi over 4. Okay, so pi over 4, when we're given pi over 4, we know it's in radians. Okay, and we are going to be working with radians quite a bit in this unit, so we might want to review for special triangles. If we have radians, we can use special triangles in order to come up with exact values for some of the most popular angles. Okay, so this particular one here, let's see if I can change the color, is our special triangle where we have pi over 4. Okay, and this is 90 degrees. Okay, so pi over 4, so we have here is 1, 1, root 2. So I call this the 1, 1, root 2 triangle. I just like to sketch out my special triangle. You can also use Pan's hands, which I have posted a little cheat sheet on how to use Pan's hands. Okay, so in this case here, we can use any of these. Let's just use this one. If we want to do cosine, remember SOHCAHTOA. SOHCAHTOA. Okay, so cosine is adjacent, so 1 over root 2. So the cosine of pi over 4 is equal to 1 over root 2. Okay, if you wanted to rationalize that, it would be root 2 over 2. So 3 root 2 over 2. Okay, and that would be my slope, pi over 4. Of course, to finalize, you would just then give me a therefore statement. Okay, and I'll let you do that. We need example number 2. We want to find the equation of the tangent to the curve of f at x is equal to negative sine of x at the point where x is equal to pi over 6. Okay, so in this question we want to find y is equal to mx plus b. So the first step is to find the slope, which we need to find the derivative. So the derivative of negative sine x is negative cosine of x. Don't forget the negative. The negative is just a coefficient up front, negative 1. Sine of x is cosine of x. Now we will need our other special triangle. Okay, or you can use Pan's hands. I'm just used to using this. Okay, and our special triangle here is pi over 6, pi over 3. Okay, so just as a refresher, this is 60 degrees, 30 degrees. Okay. Okay, so it's the 2, 1, root 3 triangle. Okay, in this case, we want to find cosine of pi over 6. So this is our angle of interest right here is pi over 6. Okay, cosine again, SOHCAHTOA. Cosine of pi over 6 is equal to adjacent over hypotenuse, so root 3 all over 2. Okay, so then subbing this back in, pi over 6 is equal to negative root 3 over 2. Okay, so that's our slope. M then is equal to negative root 3 over 2. Okay, so we have x, we have m, we need y. Okay, so y, going back into our original function here. Okay, so we're going to say y then is equal to negative sine, this would be a negative, so sine of pi over 6 is opposite over adjacent, which is a half. Okay, so y then is equal to negative a half. Okay, so negative a half, let's plug it back into y is equal to mx plus b, is equal to negative root 3 over 2. Yes, it is going to be a little bit sloppy, but that's okay. Pi over 6, okay, plus b. So negative a half is equal to negative pi root 3 over 12 plus b. Okay, so changing to common denominators, negative 6 over 12, moving this over, plus pi over root 3 over 12 plus b. And then finally, pi over root 3 minus 6 all over 12, oops, equals to b, equals to b. Okay, and that's b. So y then is equal to negative root 3 over 2 plus pi root 3 minus 6 over 12. Okay, so it is a bit sloppy. That is a 3 there as well. Let's see. Okay, and also we've forgotten our x here. Okay, and that looks like all we're able to do. The only thing we could do is maybe simplify the fractions, but basically that's our final answer. Okay, and that concludes our lesson for today, and we'll see you next time.